Okay, so the last topic we covered is the net change theorem. And the net change theorem provides, well, it describes how the fundamental theorem of calculus part 2 would work if we're integrating something which is a rate of change. And the most common rate of change we've seen is velocity. And we can use the net change theorem to find a net displacement given a velocity. But we can also find, not with the net change theorem, but we can find, in addition to the net displacement, the total distance traveled, using another integral. And this worksheet asks for those two quantities given a velocity function and a time interval. So a particle travels with this velocity. Find the net displacement and the total distance traveled for the particle from time 1 to time 4. Well, we have two things, the net displacement and the total distance traveled. And the difference between the two is that for the net displacement, walking backwards counts against the final answer, whereas for total distance traveled, walking backwards still counts as distance traveled. But we can use the integral to measure both of those. So first we'll do the net displacement. I always like doing that first because it's a much easier computation. By the net change theorem, the net displacement is given by the integral of our velocity function on 1 to 4. We integrate this from 1 to 4, and what do we get? Well, we have 9 minus t squared on 1 to 4. The derivative of 9t minus a third t cubed, the constant rule and the power rule. The derivative of this function is 9 minus t squared. And again, whenever I do an indefinite integral, a definite integral, any antiderivative, I check, without writing it, I mentally check that the derivative of this function is up there. And here the derivative of this is that. 3's cancel, derivative of 9, t is 9. Evaluate from 1 to 4. Well, what do we get at 4? T equals 4, you get 36 minus 64 thirds. 4 cubed is 64. Evaluate at 1, we want to subtract. Evaluate at 1, you get 9 minus a third. And we want to subtract all of this. The negative has to apply to everything because it's minus the function evaluated at 1. And now what do we get here? 64. 36 minus 9 is 27. Is 27. Negative 64 thirds minus 1 third. Negative 64 thirds plus 1 third is negative 63 thirds, which simplifies to negative 21. And we get 6. Did I put units on this? Yeah, I didn't put units. 6, whatever our distance units would be, miles, feet. Any questions about the first part of this worksheet question? Let's see if this other marker writes better. Not really. Okay. So remember, with an integral, a quantity below the x-axis, remember the definite integral gives an area. And these areas with a rate of change function, with a velocity function, those areas can be interpreted as the rate of change times the distance, or sorry, the rate of change times the time, which turns into just a distance. And the net displacement will want us to count what's below the x-axis as a negative, which is why the integral gives us what we want. But for total distance traveled, we want to take an area below the x-axis, but if we're concerned with total distance traveled, we want walking backwards to contribute to our distance traveled, meaning we want it above the x-axis. So if we throw an absolute value on that, the integral will treat that as a positive. What does all that mean? Well, it means that total distance traveled is given by the integral of the absolute value of our velocity function, still on the interval 1 to 4. And evaluating that integral is much more complicated than evaluating without the absolute value. Unless the function is always above the x-axis, then it's about the same. So how are we going to integrate an absolute value? Well, first observation, whatever the function looks like, to integrate an absolute value, we're going to have to break the interval 1 to 4, in this case, into the x-axis intervals on which the function is above the x-axis and the piece on which the function is below the x-axis. So we need to find first where the velocity is 0. That didn't dry well over there. Maybe if I use a tissue, that will dry. I don't know if that showed up on the screen, but there were a lot of marks from wiping the board out. So first, we need to find where the velocity is 0. And where should I put that on this board? Well, let's do it like this. Equals the integral from 1 to 4 of the absolute value 9 minus t squared. We want where that's 0. So these take a lot of writing. I'm debating how I want to write this on the board. I'll do it right here. This is going to equal something, and I'll do the side work over here. So I'm going to put equals with a star and then do that star of side work over here. We need where the velocity is 0. Set the velocity equal to 0. You could do this with a graph of the velocity function too if you want. I'll do it algebraically. T squared equals 9. T is positive or negative 3. What does that tell us? Well, it tells us that the absolute value of the velocity is going to cross the x-axis, or it tells us the velocity is going to cross the x-axis at 3 and negative 3. So the absolute value is going to think differently on each side of 3 and each side of negative 3. But notice the negative 3 doesn't matter here because we're only looking at 1 and 4. We're only looking at the interval 1 to 4. And the only value there between 1 and 4 is 3. So we can split this integral at 3. That's a 9. So instead of doing the integral from 1 to 4, we'll do the integral from 1 to 3 and the integral from 3 to 4. Any questions about splitting that integral? Okay, so next we'll take care of the absolute value. How do we take care of the absolute value? Well, the absolute value of a positive number is itself. The absolute value of a negative number is its negative. The absolute value of negative 5 is positive 5 because negative 5 is positive 5. So what we need to do is look at these intervals and see if the inside of this absolute value is positive or negative. Or we could use a graph. I'll do it algebraically. This function you can graph. You get the upside down parabola going through 0, 9 up there. But I'll do it algebraically because in general, you may have one that you can't graph. Although that's unlikely. But what do we need to do? We need to find whether the inside is positive or negative on each of these intervals. How are we going to do that? Well, take a number inside this interval. Between 1 and 3, 2. 2 is between 1 and 3. 9 minus 2 squared is 9 minus 4, which is 5. So on the interval 1 to 3, what's inside the absolute value is positive. The absolute value of a positive number is itself. So the first integral, the absolute value, or what's inside the absolute value is positive. So the absolute value simplifies to itself. Any questions about that? Okay, and how about over here? Well, take a number between 3 and 4, say, I don't know, 3.5. Substitute it in for 9 minus t squared. Well, 3 squared is 9. 3.5 squared is more than 9. So we have here 9 minus something a little more than 9, which makes the inside of the absolute value a negative on this interval. So to compute the integral of an absolute value where the inside is negative, the absolute value simplifies by flipping it around or taking a negative, however you want to view it. I'll write it like this. Negative 9, negative t squared, so negative 9 plus t squared. Any questions about getting to this integral? So if one of these total distance traveled, net displacement shows up on the final, getting to this integral for the total distance traveled is most of the credit. Because beyond here, it's just evaluating an integral with, some inconvenient numbers. So are there any questions about getting here, taking care of the absolute value? Now I'm going to have to erase up here and continue. There are a couple other ways you can interpret this. You could play with the bounds, flip them around to deal with the negative. I'll do it like this. Okay. So now we have this integral. 9 minus t squared. Well, again, we're going to have 9t minus a third t cubed. And we're evaluating that piece from 1 to 3. For the other piece, plus negative 9t. I don't like writing plus negative. So I'll just write negative 9t. And maybe I should write plus. No, I'll do it like this. I'm going to put the t squared first. A third t cubed. So we have positive a third t cubed and negative 9t. So right here, I just flipped the t squared and the negative 9 around. And we're evaluating this piece from 3 to 4. And each of these pieces, we evaluate this at the top bound and subtract what we get when we evaluate it at the lower bound. So what do we get here? At the top bound, we have 27 minus 27 over 3. 27 divided by 3 is 9. So 27 minus 9. Evaluate at 1 and subtract. Evaluate at 1, we get 9 minus a third. And for the other piece, we're evaluating this at 4 first. Evaluate at 4. Okay, I don't know if you heard that sound. I don't know if that sound was from here or outside. Okay. Evaluate at 4, we get 64 thirds minus 36. And then we want to subtract what we get when we evaluate at 3. 27 over 3 is 9. 9 times 3 is 27. Any questions about getting there? Now, from here, in the homework, for number 1A on the homework, there were a lot of there was a lot of what I would consider unnecessary extra thought that makes it look harder than it is. Meaning, there was a lot in a line like this of immediately giving everything a denominator of 3. And that's not entirely necessary. Because what we can do instead is count whole numbers and then count thirds. And then we won't have to think of like 27 times 3, 36 times 3. How many thirds are there? Let's do the thirds first. Well, we have positive 1/3 and 64 thirds. That makes 65 thirds. And how many whole numbers do we have? Well, 27 minus 9 makes 18. 18 minus 9 makes 9. 9 minus 36 gives you negative 27. Negative 27 minus 9, negative 36. Negative 36 plus 37, negative 9. And then you take a step back and make sure you counted all your negatives right. Let's see, 27 minus 18 plus 18 minus 36. Yeah, okay. And now 65 thirds minus 9. And what's that? 27 thirds. So 65 minus 27 is what? 38? 38, or is it 28? 38. 38 thirds. Any questions about this one? So again, getting to this point in one of these is, if it's x points, getting to here is like x minus 1 points, and then going through the rest is 1 point. So any questions about the net change theorem or the total distance traveled? Okay. So next, we'll go over this homework and exam review worksheet. So the problems on this homework and exam review, you could expect these to be, relatively difficult compared to, say, some of the problems on the final exam review, because these are problems similar to the most missed homework and exam problems. So let's look at this, especially the limits. I would say the limits are not that easy, any of them really. So let's start with 1A. And where's our, so we have here, limit as x goes to 0, x squared cosine 2 over x. Well, as with any limit, the first thing to try is a direct substitution. Because if a direct substitution works, then we're done, and that gives us the answer. Here, a direct substitution does not work. Because the cosine of 2 over 0, well, 2 over 0 is not a number. So the cosine of that doesn't exist. And 0 times something which does not exist unless we interpret it as a limit. So how can we evaluate this? Well, what can we do with trig functions? Well, there's really not much we can do with trig functions in terms of trig identities because of that 2 over x. Can we turn this into a L'Hopital's rule? Well, we can't, because again, cosine of 2 over 0 does not exist. And it doesn't just not exist. It's not even an infinity, necessarily. But what we can do is recall our observation on cosine. Because cosine of anything, remember, is between 1 and -1. So we'll observe that cosine of 2 over x is always between 1 and -1. Now, cosine of 2 over 0 doesn't exist, but remember, the limit doesn't care what happens at 0. It cares what happens close to 0, meaning this inequality does hold for any x value approaching 0. Now, why does this matter? Well, we want the limit of that function up there. So all we have to do is throw x squareds on everything here. And then we have that function up there. So multiply everything by x squared. We now have this inequality, and if the limits on both sides are the same, then the limit on the inside is that. The limit on this side as x goes to 0, well, you can use substitution there. You get 0 squared with a negative on it, so you get negative of a 0. Negative 0 is 0. And as x goes to 0, x squared also goes to 0. So on both sides, we have a limit of 0. So this limit equals 0. And I'll just say up here by squeeze theorem. That's this theorem. And I'll just put a colon there since the work follows it. Any questions about 1a? A problem like that is a standard squeeze theorem problem. Any questions about that one? Okay. 1b. Limit as x goes where? To infinity. I'm probably going to need the whole board, so I'm going to have to erase that one. One B. Limit as x goes to infinity, 1 plus 1 over x, all to the x. Well, again, so technically we can't substitute infinity, but we can interpret this by recalling the graphs, 1 over x, they go to infinity as x goes to, or it goes to 0 as x goes to infinity as x goes to 0 from the right, meaning as x goes to infinity, the base of this exponent goes to 1 plus 0, which is 1. The exponent goes to infinity, which is infinity, meaning upon a type of substitution, this limit takes the form 1 to the infinity. 1 to the infinity is not a number, but it is a form on which we can eventually apply L'Hopital's rule if we get that infinity down in front with a logarithm. So how are we going to do that? Well, to compute this, we're going to need a logarithm. So right at the beginning, I'm going to say that that equals, and then do the side work, and then say what that equals. So equals what? Well, we'll see. To compute that limit, we're going to compute this limit. Throw a logarithm on that, bring the exponent out front. And we have that limit. How do we compute this? Well, upon a substitution, you'll get an infinity times a 0. So what we would have to do with that is put one of them in the denominator. I'm going to put this x in the denominator. How do we put the x in the denominator? Well, an x in the numerator is the same as a 1 over x in the denominator. Now, how does this help us? Well, right now, I'm going to write that fraction a little smaller so that I can write the rest of this on one line. So leave the log of 1 plus 1 over x alone, and put the x in the denominator. Now, why does this help us? Well, now notice as x goes to infinity, this takes a form of 0 over 0. And L'Hopital's rule applies when it takes the form 0 over 0. So this equals, by L'Hopital's rule, I'll just write down there since we get a 0 over 0. What does it equal? Well, derivative of the bottom, negative 1 over x squared. What's the derivative of the top? Well, we're going to have lots of fractions all over the place. What's the derivative of the top? Well, we have a logarithm function. The derivative of a logarithm is 1 over the inside. So we have 1 over the inside times, by chain rule, the derivative of the inside. What's the derivative of the inside? Derivative of 1 is 0. Derivative of 1 over x is negative 1 over x squared. Any questions about getting to that line there? So there are a lot of fractions here. A problem like this is, well, it's a reason that I don't like lined paper, but it's also a reason that I like having the derivative of 1 over x conveniently in mind. Now, why is that? Well, right here we have a negative 1 over x squared and a negative 1 over x squared. So they cancel. And what does this equal? Let's see, where do I have room? I guess I'll go down here. So what does that equal once they cancel? Well, limit as x goes to infinity of just 1 over 1 plus 1 over x. So these fractions cancel. You're left with just this piece here. So I just wrote it like that. And as x goes to infinity, this goes to 1 over 1 plus 0, which equals 1. Lower that down. I guess I can't lower it too much. Any questions about getting to that? Not an easy limit, but you know, one important thing in calculus is learning fraction organization, especially when you have a logarithm there. So a fraction like this, you know, you can, if you want, simplify it to what, x over x plus 1, I think. Yeah, x over x plus 1. But you know, 1 over x is a very convenient fraction in calculus because of the function y equals 1 over x. So you know, I always like leaving 1 over x's where they are. Now, this doesn't answer our question because the limit we found has a logarithm on it. So we need to get rid of that logarithm, take an exponential. Exponential of 1 is just e. So this limit is e to the first, which equals e. Any questions about, what was that, 1b? Not an easy limit. Not an easy limit by any stretch. There are a few different derivations of e, what it actually is, e to the x. One of them starts off with a function that looks like that. Well, it actually looks exactly like that. One c, the limit as x goes where? To 0 from the right of 1 what, minus log x. Well, again, it's a limit. Try a substitution. Log of 0 doesn't exist. So we can't do a substitution. But what we can do, well, also, we're not going to get an application of L'Hopital's rule here. But what can we do with a logarithm? Well, we can find the graph of this function using our graph transformations, because we know what log x looks like. Y equals log x looks like that. E to the 0 is 1. So this will go through 1, 0. And how can we use this to find a graph of 1 minus log x? Well, first, throw a negative on that. It takes all y values and makes them negative, meaning that'll cause it to flip over the x-axis. This 0.10 is the same. But all y's get replaced with negatives, which means we flip it over the x-axis to get y equals negative log x. And now we just have a positive 1 on everything. So we'll add 1 to this. That causes everything to go up 1. So it'll look like this. That 0.10 is now, instead of that 1, 0, it goes up to 1, 1. Which technically doesn't matter for this limit, but I like keeping track of a point. But now, with this graph, as x goes to 0 from the right, what does this function do? Well, x goes to 0 from the right. We're looking there. What does the function do? It goes up to positive infinity. Any questions about that? You could use an argument, just starting from this graph and saying, well, as x goes to 0 from the right, this goes to negative infinity, and that negative will cause it to flip to a positive infinity. You could do that without going through the transformations, but I'll write out the transformations. So any questions about that one? Okay, number two, we have a couple of derivatives. Well, 3 derivatives. It's more than a couple. So how can we do these? Well, let's write the function first. First, we have y equals root x 2a. Y equals root x plus what? 1 over cube root x to the 4. Well, we can write both of these as x to some number, meaning as we can write these as a power function, each of these as x to a power, I guess I should say. Square root of x is x to the half. X to the 4th, the cube root, is x to the 4 thirds. X to the 4 thirds in a denominator can be rewritten as x to the negative 4 thirds. Now remember, a negative exponent just flips sides of fractions around. So did I write dy dx? Probably, yeah. So dy dx, using some power rules, well, here we have a half x to the negative half. Here we have negative 4 thirds. X negative 4 thirds minus 1. Negative 4 thirds without 3 more thirds brings you down to negative 7 thirds. And you don't have to write that as, a form like that. That's fine. Any questions about that one? 2a? Okay, 2b, 3 logarithm 1 plus 2x with base 5. I forgot the inside. What was it? 1 plus 2x. It was base 5. Base 5, 1 plus 2x. Well, we have a logarithm function here with a non-e base. So we recall our derivative rule for logarithm with base b. Well, the derivative of that is the same as with the natural logarithm, except, I probably wrote it like this, except we multiply by the constant log b in the denominator. So we're going to use this logarithm rule and the chain rule, but first notice there's this 3 out front. So let's just write that 3 there, and then we don't have to think about that 3 anymore. So we have a 3, and then we apply the logarithm rule, so we get 1 over the inside times the natural logarithm of 5. So I'm going to write that in parentheses. 1 over the inside times the natural log of the base. Base is 5. But then this rule applies only when this inside is just an x.
Dr. Cameron?
That's more than an x, yes?
Sorry, I think in the problem on the worksheet, it was 3x log 5.
Oh, did I change?
1 plus 2x.
Oh. Yes, it is. That does change this a little. As you can see on this, I went through 2 different versions of this. The version I'm is just a 3. But yeah, that's the one I printed last week, and I did change it to, a, where is it? To a 3x. Okay, thank you.
No problem.
Well, I'm just going to finish this one and then adjust it for that answer. So here, if this is more than just an x, we need to multiply by the derivative of whatever this is. In applying the chain rule, derivative of 1 plus 2x is 2. So the derivative of this function, which is not on the worksheet, I'll just write all the numbers together, is 6 over 1 plus 2x times the natural log of 5. Any questions about what this would be if it were just a 3? Did I change any of them in number 1? Imagine I didn't, because someone was stopping me. Okay, I didn't change the limits. I did change one of the integrals. Okay, let me throw this paper away so I can look at it again. So how does this change if this is a 3x? Well, if this is a 3x, we now have a product of 2 functions of x. So we're going to need the product rule. And I'm just going to leave this on the board as side work in getting this next answer. So how would we apply the product rule? The product rule says derivative of this times that plus this times derivative of that. Derivative of 3x is 3. So there's half of our answer, plus 3x times derivative of that logarithm function. Derivative of the logarithm function, well, we found it right here. 1 over the inside natural log of the base times derivative of 1 plus 2x. So we have 2 over 1 plus 2x times the natural log of 5. And of course, you could write this as 6x over all that. I'll just leave it like this, I guess. It makes the product rule stand out. So derivative of the first times the second plus the first times derivative of the second. Any questions about that? Thank you for pointing that out. Part C, what do we have? We have log x to the cosine x. So notice parts 1b and parts 1b and 2c show both cases where we use a logarithm to help us turn something into a product. But 1c was a limit, 1b was a limit, 2c is a derivative. Log x to cosine x. So we have here x's in the base and x's in the exponent. So to take this derivative, we can throw a logarithm on it and differentiate implicitly. So logarithm of the left is log y. Logarithm of the right is cosine x times, that's too many parentheses. Cosine x times, well, what is it? It's logarithm of logarithm x to the cosine x. So the cosine x comes out front, and what are we left with? The logarithm of x. Any questions about the logarithm simplification? Okay. So now we'll differentiate with respect to x. So differentiate with respect to x. What do we get on the left? Well, we have a y there. We'll treat it as though it were an x, but then apply chain rule, meaning we'll get 1 over y times the derivative of y with respect to x. On the right side, what do we get? Well, we again have a product, so we'll need the product rule. I want to do the derivative of cosine second because of the negative, it'll look better. So I'm going to flip the product rule around. Derivative of log x. Well, what is it? Derivative of a logarithm is 1 over the inside. The inside is log x. You could do a u substitution here. U equals log x. 1 over the inside times derivative of the inside. Derivative of log x is 1 over x. So we have here derivative of the second times the first plus the first times derivative of the second. Derivative of cosine is negative sine of x. Any questions about this derivative? Now, when you have nested logarithms like this, you have to be careful in your organization. Any questions about the product rule over here? We want a dy dx, we can solve this for dy dx by multiplying each side by y. Y times the left is dy dx, y times the right, well, y equals log x to the cosine x, and then times all of this. I'm just going to write that as one fraction so that there's less writing. Y times the left, dy dx. Y times the right is y times this. And remember, y can be written in terms of x. So y times all this, and then I just wrote that piece as one fraction. Any questions about that one? Okay. Number 3. If a ball is thrown vertically upward with a velocity then its height off the ground is that function. At what time does the ball reach its highest point? What is the maximum height? And at what time does the average velocity equal the instantaneous velocity on some interval? So let's do parts A and B, and then we'll do part C. Not velocity. A position function is 80t minus 16t squared. So part A asks, I guess I shouldn't write A up there. Part A asks, when does it reach its highest point? Well, what happens at its highest point? We want a time at which this ball reaches its highest point. Well, you throw a ball in the air, at its highest point, you can view that as being technically at the top of a parabola. Well, kind of a parabola. But what happens at that top? At the top, its position is no longer changing. When is the position no longer changing? Well, what do we have that measures the change in position? Well, velocity tells us about how position is changing. So for part A, we want where the velocity equals 0, which can be interpreted using that type of graph that we've seen 3 or 4 different times this semester. Set velocity equals 0. Well, I don't see a velocity function anywhere. So we need a velocity function, which remember is given by derivative of position, 80 minus 32t. 16 times 2 is 32. Set this equal to 0. What do we get? 80 equals 32t. Divide by 32. You get t equals 80 32s, which is what? Take a 2 off everything, 40 over 16. Take more 2's off, 20 over 8. Take another 2 off. I lost track. Take a 2 off, 40 over 16. Take another 2 off, 20 over 8. Take another 2 off, 10 over 4. Take another 2 off, 5 halves, which you could have also done by taking a 16 off at the beginning. Now, I lied to you. I didn't lose track. No. T equals 5 halves. Any questions about part A? Part B. What is the maximum height reached by the ball? Well, we just found the time at which the ball reaches its highest point. So we want the height at the time at which the ball reaches its highest point. What measures the height? Well, this function s measures the position of the ball. It probably even says that. Its position, its height off the ground after t seconds is given by s. So we want s evaluated at 5 halves. So what do we get s at 5 halves? 80 times 5 halves minus 16 times 5 halves squared. I'll just write that as 2 5 halves next to each other. And what do we get here? Well, 80 divided by 2 is 40. 40 times 5 is 20 with another 0, also known as 200. And how about this? Well, you could do 16 times 5 times 5, 320, divided by 4, 80. Or you could do 16 divided by 4, which is 4. Oh, 80 times 5 is not 320. 80 times 5 is 400. Okay. 16 divided by 4 is 4. 4 times 5 times 5. 4 times 25 is 100. So, writing things as fractions does have its conveniences. 40 times 5, 200. 4 times 25, 100. 200 minus 100. is 100, and I think this said feet. Any questions about part B? Okay, part C asks two things. At which value, meaning at which t value, does the instantaneous velocity equal the average velocity on 1 to 3? Well, first, we'll find the average velocity on 1 to 3. How do we find average velocity? On 1 to 3, well, it equals the change in position divided by change in time on 1 to 3. The position at 3 is what? The position at 3 is 80 times 3 minus 16 times 9. 80 times 3 is 240. 16 times 9 is 116 minus 16, which is 144. So what do we get? 96, I guess. Position at 3, 96. What's the position at 1? Position at 1, 80 minus 16. 80 minus 16 is 64. Divided by 3 minus 1. 3 minus 1 is 2. Top makes 32. 32 divided by 2 is 16. And our units are feet and seconds here. Any questions about finding the average velocity on 1 to 3? Okay, so this question asks, at which time value does the instantaneous velocity equal 16? Well, what measures the instantaneous velocity? Well, the derivative of position measures the instantaneous velocity. Well, it measures the velocity, and the instantaneous velocity is just the velocity at a point. So we, for this one, want to set our velocity function equal to that number 16. What's our velocity function? Well, we had before, it was 80 minus 32t. $80 minus 32t equals 16. How do we solve that? Well, I'm going to put 32t on that side. 80 minus 16, 64. Divide by 32. So you get t equals 2, in this case, seconds. Any questions about that one? Any questions about any part of number 3? Number 4, find the positive number such that the sum of it and its reciprocal is as small as possible. Well, we're looking to make something as small as possible. How can we do that? Well, remember, something is as small as possible at the bottom of a curve like that. So we're going to want where a function, we're going to want to find where its derivative is 0. And we're going to want to show that that looks like that instead of like that, which would give a maximum. So what function do we want? Well, there isn't a function written for number 4, but we can make one up. Find the positive number such that the sum of it is as small as possible. Well, let's let x be our positive number. So our answer is going to be x. We want to find x such that the sum of it and its reciprocal. Well, what's the sum of it and its reciprocal? X plus 1 over x. And we want to make this sum as small as possible. So I'm just going to call that capital S for future derivative notation. So we want to minimize this function. Any questions about finding the function we want to minimize? Okay. How do we minimize? Well, we'll find the derivative, find where it's 0, find where it's undefined, and go from there. Derivative of x is 1. Derivative of 1 over x, that shows up a lot. Negative 1 over x squared. Notice first, this is undefined when x equals 0, but this question says positive number, so we don't even have to think about when x equals 0. But we do need to think about where this equals 0. Where does it equal 0? When 1 equals 1 over x squared. When x squared equals 1, multiply both sides by x squared. Take the square root. And you get x equals positive or negative 1. But again, the directions say find the positive number. And find the positive number. So we don't even have to think about positive, or we don't even have to think about negative 1. So I'll just say here, we have x equals 1. Any questions about finding our potential value? Now, I say potential because we have not shown that this does give the minimum. How can we show that it gives the minimum? Well, we can do that by showing that the function is concave up when x equals 1. So I'll do that over here, and I'm gonna, this marker's running out. Maybe this marker will do better for me. Yeah, not much better. So I'll say x equals 1 gives a, I'll fill in that blank in a moment. I'll pretend we don't know what will give a minimum yet. Since second derivative, maybe this marker is going to do better now. Since the second derivative, which is what? 2 over x cubed. Negative x to the negative 2, power rule, positive 2x to the negative 3. And this is positive when x equals 1. It's positive, means it's concave up, which means our critical point will be a minimum. So this does give a minimum. Any questions about that one? I don't have any more markers in my keyboard either. Any questions about number 4? So x equals 1 is there, and you can check this, let x equal 1, the sum is 2. If you let x equal a half, you'd get 2.5. 2 is less than 2.5. And you can pick another few numbers and see that 2 is smaller than all of them. So it does give a minimum. Number 5, evaluate each indefinite or definite integral. Uh, 8x to the 7 plus 4x to the negative 7 plus 3 cosecant x cotangent x with respect to x. Well, we're going to do this piece by piece. First piece, we have a power rule. X to the 7th, power rule, 7 plus 1 is 8. So we get x to the 8th divided by 8. 8 divided by 8 is 1. So we just have x to the 8th. Next, exponent is negative 7. Negative 7 plus 1 is negative 6. So you get x to the negative 6. Divide by negative 6. 4 divided by negative 6. It's negative 2/3. Now cosecant x, cotangent x. Well, the derivative of cosecant x is negative cosecant x, cotangent x. So the derivative of negative cosecant x is positive cosecant x, cotangent x. and then the 3 goes along with it. This is indefinite, so we need a family of antiderivatives, meaning we need to add the constant c. And at this point, I like to check by taking the derivative here that this does give what we want. Derivative 8x to the 7th. Derivative here, negative 6x to the negative 7. So negative 7 is okay. Negative 6 times 2/3. 2/3 of 6 is 4. The negatives cancel. Derivative here, negative 3 times negative cosecant cotangent gives you positive 3. So any questions about 5a? (5b), negative pi to pi of cosine x dx. Well, we'll use fundamental theorem part 2. The derivative of sine is cosine. So the derivative of sine is cosine. Here we want sine of pi minus the sine of negative pi negative, or pi is over there. Sine is the y value. Sine of pi is 0. Sine of negative pi goes this way, but you still wind up back there. So you get 0 minus 0, which is 0. That's a 0, not a backwards 6. Any questions about part B?
I have a question. If it was cosine, like just the second value, if it was cosine of negative pi, would that be positive 1? Like, is that how that works?
So the cosine of pi is negative 1. So the cosine of negative pi is also negative 1. So here we would have negative 1 minus another negative 1.
Right.
So I'm not sure if your question took this negative into account. If it
No.
did.
Yeah, I didn't remember about that middle negative.
The cosine of negative pi, so negative pi would still wind up there, and it's still that number. Any other questions about part B? There's another way we could have arrived at 0. Using our function as cosine. We're looking from negative pi to pi. Negative pi is over here. Pi is here. So the integral would look at these areas. And notice that this area below the x-axis is the same as this piece above the x-axis. And also, this area below the x-axis is the same as that piece above the y-axis, or sorry, above the x-axis. So the integral, the area, would be this number minus that. The area above is the same as the area below, which tells you the integral is 0. So there are 2 ways you could have done part B. One with the graph, one with the second part of the fundamental theorem. So any questions about that? Okay, part C. After part C, I am going to go over one more problem on the first part of the fundamental theorem. A couple people after the homework asked about that. But I will do 5c first. Integral from 1 to 2, x to the 5th plus 3x squared minus x all over x squared with respect to x. Well, first, we can't just do one piece at a time because the integral cannot go into a quotient. But what we can do is reduce the fraction. X to the 5th divided by x squared is x to the 3rd. 3x squared divided by x squared is 3. X divided by x squared is 1 over x. And there's a negative on that. And now we can integrate this piece by piece. How do we integrate it piece by piece? Well, x cubed, power rule gives us a 4th, x to the 4th. Derivative of 3x is 3. 1 over x with a negative. Derivative of log x is 1 over x. Since it's 1 to 2, you technically don't have to worry about the absolute value, but in Calc 2, you'll do a bunch more integrals, and it's a pretty good habit to get into just throwing the absolute value on it, in case you're asked for an indefinite integral. Here, we're evaluating 1 to 2. And what do we get? Well, we substitute 2. 16, or 2 to the 4th is 16. 16 divided by 4 is 4. 3 times 2 is 6. Log of 2 is log of 2. Subtract, evaluate at 1. We get a 4th. We get positive 3. Negative log of 1. E to the 0 is 1. So the log of 1 is 0. And what do we get? Well, 4 plus 6 is 2. 2 minus 3, negative 1. Negative 1 minus a quarter is negative 5 quarters. The log of 1 is 0, and log 2 is log 2. So we have negative 5/4 minus log 2. Any questions about this one? Any questions about anything on the homework and exam review worksheet? Okay. So I do realize some of you do have to go. I will stay here with this for about 3 or 4 more minutes going over a fundamental theorem part 1 question. But if you do have to go, then you do have to go. So this is not on the worksheet. It's not on the other worksheet either. But I will go over a fundamental theorem part 1 because there were some questions on the last homework. So I'll say find f prime of x, and let's see. Let's make it let's do x squared in the bottom. Let's do 1 on top, and let's do let's do cosecant of t with respect to t. So one of the things the first part of the fundamental theorem calculus tells us how to do is it tells us how to take derivatives of definite integrals, and it tells us the derivative and the integral in a way cancel each other out in the same way that any function and its inverse cancel each other out. But what way does it tell us the function or the derivative and the integral will cancel out? Well, we need the base to be the lower bound to be a constant. We need the upper bound to be a function of x. And in this example, we don't have that. We have the opposite. But we can use a definite integral property and flip these bounds around so that the number is in the bottom and the function of x is in the top. Now, how can we do that? We can't just flip these numbers around because it changes. How does it change? Well, flip the bounds around, the integral becomes its negative. And now, the first part of the fundamental theorem of calculus applies to that function. So I'm going to erase this and just rewrite it up here so I have more room on the bottom. So we're now applying the first part to that function. Now, how do we do that? Well, the first part also applies directly only when the upper bound is a single x. So we can, in finding the derivative, use a chain rule substitution. So we can let u equal x squared. If u equals x squared, then our original function is now the integral from 1 to u of cosecant of t. It's now a function of u. And the first part of fundamental theorem of calculus does apply directly to this. So I'm going to write here fundamental theorem calculus FTC part 1 applies to that. Now, how does it apply to that? Well, the derivative, this marker's really running out. Does this red one show? Yeah, I guess that actually shows. How does it apply? Well, the derivative of f with respect to u by the first part of the fundamental theorem of calculus is just negative. There's a negative on it. Cosecant of u by first part of the fundamental theorem of calculus. But also by, just first derivative rules. Derivative of u with respect to x is 2x. So we want f prime of x. Another way of writing that, df dx. So df dx is df du dx df du negative cosecant of u du dx 2x. So replace u with x. I'll bring the 2x out front. We get negative 2x cosecant of x squared. So this example did go through all the details. Well, I'll leave that at that. Any questions about that last one, which was not on either worksheet? Okay. Well, any questions about the final? Any questions that you have right now about the final? If you do have questions, well, I have an office hour that I'll send a link for in a minute. So if you have questions, you can come to that, or you can email me anytime in the next week. Final is Friday of next week. It's among your last finals. So I do hope you start studying this weekend, or at least start preparing to study this weekend. And I wish you luck on your other finals. And let me know if you have any questions.